let us move to the second part where I want to give you a brief overview of the history of magnetism. Magnetism has been known for thousands of years. It was already present in ancient Mesopotamia and ancient Egypt, where lodestone was given the beautiful name of living metal. The first magnetic artifact is probably the lodestone geomantic compass that dates back to the Olmec civilization about 3,000 years ago. Ancient artifacts have also been made in ancient China about 2,000 years ago, such as the south pointing spoon, which is a spoon that points systematically toward the south, or the Manchon chariot. From the scientific perspective, the first contributions that describe the magnetic property of matter are attributed to Wang Hong and Thales of Miletus about 600 years before Christ. In spite of this very old history, our understanding of magnetism has made a humongous progress in the past 200 years only due to the development of the theory of electromagnetism and the discovery of the quantum electron spin. So now, let me give you my personal view of the recent history of magnetism.
Everything really started between the 18th and the 19th century by the amazing work of scientists such as Gauss, Ørsted, Biot, Savart, and Ampere. Those scientists conducted experiments to determine the connection between the electrical currents and magnetic fields. The 19th century saw the unification of these various physical concepts with the birth of classical electromagnetism led by Maxwell, Lorentz, Tesla, and Hertz. But the birth of magnetism can be really traced back to the beginning of the 20th century with the work of Weiss, Langevin, Curie, Landau, Van Vleck, and Néel. These scientists developed very powerful classical and quantum concepts to describe the behavior of magnetic materials. The microscopic description of magnetism benefited remarkably from the contemporary development of quantum mechanics in the early 20th century. The quantum theory, which is now at the foundation of modern physics, has been developed by a large group of visionaries like Planck, Einstein, Bohr, Heisenberg, Pauli, and many more. But as far as magnetism is concerned, the most influential breakthrough of quantum mechanics was undoubtedly the discovery of the quantized spin angular momentum by Stern, Gerlach, Uhlenbeck, Kramers, Koenig, and Gutschmidt. I do not claim that this very personal historical perspective is exhaustive, but I believe it illustrates nicely the evolution of our understanding of magnetism, from the discovery of electromagnetism to the quantum spin. Let us now take a closer look at the discoveries made during the past century. It starts in 1907 with the introduction of the molecular field theory by Pierre Weiss. This classical theory gave a first glimpse on some of the important features of magnetic materials. About 15 years later, the discovery of the electron spin by Uhlenbeck, Gutschmidt, and Koenig completely transformed the way we look at magnetism in atoms and solid state. In 1928, Heisenberg introduced his celebrated exchange model, which is now at the basis of probably 90% of the studies of magnetic systems. In 1932, Néel introduced the concept of antiferromagnetism, which are magnetic materials displaying a magnetic order but with no overall magnetization. In the 30s, two other very important achievements were made. The first one is the development of band theory based on the idea that electrons in crystal behave like Bloch waves. This description has a direct influence on the way we actually model magnetism in materials. The second important achievement was Landau's theory of phase transition. That is a classical way of looking at magnetism, but it is extremely powerful and very successful. A technological breakthrough was achieved in 1949 with the proposal of magnetic core memory by An Wang at IBM. In this device, magnetic bubbles are used to store information. About 40 years later, the introduction of neodymium iron-boron permanent magnets had massive influence on magnetic engineering and enabled the efficient conversion between mechanical motion and electric currents. In 1988, Albert Fert and Peter Grunberg discovered the giant magnetoresistance, which really marked the birth of Spintronics. Less than 10 years later, IBM introduced giant magnetoresistive reed heads for their recording applications, thereby significantly improving the data storage capabilities. At about the same time, in 1996, Sonzuski and Berger introduced the spin transfer torque, which constitutes the second revolution of spintronics. And about 10 years later, magnetic random access memories entered the market.
Now that we have seen this historical overview, let us move on and review some key concepts in magnetism. The fundamental equations one needs to understand before tackling magnetism are the famous Maxwell's equations.
So what are these famous equations? We start with the two Gauss laws. Gauss law for the electric field states that the divergence of the electric field equals the charge density, while Gauss law for the magnetic field states that the magnetic field is divergenceless. So in other words, there is no such thing as the magnetic charge. Then there is Ampere's law that connects the curl of the electric field to the time derivative of the magnetic field. And reciprocally, Faraday's law connects the curl of the magnetic field to flowing charge current and the time derivative of the electric field. So these four equations put together constitute what we usually call Maxwell's equations. And they describe the interplay between the electromagnetic field, the charge densities, and the current densities. Now, I think it's important to keep in mind that this simple set of four equations is only the final result of a long-term research endeavor engaged by Maxwell when he was in his 30s. In his original theory, Maxwell had no less than 20 equations. With time, he was able to boil them down to a set of just four equations. His major disruptive contribution, though, was to understand that magnetic field and electric field are intertwined and constitute a single electromagnetic field. To provide a comprehensive description of the electrodynamics, though, it is important to add a fifth equation. This fifth equation is called the Lorentz force equation and describes the force exerted by an electromagnetic field on a moving charge. This set of five equations is defined in vacuum. Let us now see how it changes when we consider that this interaction occurs in matter. In matter, Maxwell's equations need to be a little bit tweaked. As a matter of fact, one has to take into account three additional effects that do not occur in vacuum, only in matter. The first one is that when you apply an electric field in matter, the electronic cloud present in the material reacts to this electric field and can be displaced. The displacement is proportional to the external electric field. Epsilon 0 here is the electric constant, plus the polarization of the cloud. This polarization is also influenced by the electric field and may depend on it linearly or non-linearly. So at the end of the day, you can write the displacement as an effective dielectric constant epsilon times the electric field. The important property of these vectors is that they are polar vectors. so they are invariant under time reversal. The second effect that occurs in matter is the distortion of the electron cloud under the magnetic field, such that the external magnetic field can induce magnetic moments that modify the overall field present in the material. In addition, and this is the third effect, the material can also possess magnetic moments intrinsically. This is the case of paramagnetic, ferromagnetic, or antiferromagnetic materials, for instance. As a result of these two additional effects, the induction field B present in the material can be written as a sum of the external magnetic field plus the magnetic contribution from the induced and internal magnetic moments. The contribution of the external magnetic field is written μ0H, where μ0 is the vacuum permeability and H is called the exciting field. So you can see that the equations for the electric displacement and for the magnetic induction actually share a lot of similarities. An important difference, though, is that magnetic fields are actually pseudo-vectors, so they change sign upon time reversal. In paramagnet and diamagnets, what we are going to see in the next lectures is that the magnetic moments are directly proportional to the applied external field. And therefore, the magnetic induction is simply proportional to the exciting field H. Here, mu is called the permeability. So the question now is, what happens in magnetic materials? Well, it's complicated. Actually, because the material possess magnetic moments that are interacting with each other, they may not act linearly when submitted to an external magnetic field, and they might result in much more complex behavior that we are going to see later in this course. Now, considering the three effects mentioned previously, let us rewrite Maxwell's equations in matter. We have to write them in such a way that the displacement D and the exciting field H now appear explicitly. You see that the first equation is Gauss' equation applied to the displacement field, not the electric field anymore. The second and third equations don't change because the induction field remains well defined. And the fourth equation now does not involve the induction field B anymore, or the electric field E, but rather the exciting field H and the displacement D. These are the four equations that we are going to consider in matter. Now I'd like to move to the second important concept in magnetism, which is the classical magnetic dipole moment. Since the 19th century and Faraday's law, it is known that electric currents circulating in loops can create magnetic fields. Well, it turns out that in classical mechanics, as you may remember, rotating objects are characterized by their mechanical moment. So, it is tempting to associate a magnetic moment to rotating charges. Here is just an example. If you consider electrons circulating around a closed loop, you can associate a moment to those rotating charges. So this moment, mu, should simply be written as q over 2 r squared omega, where q is the charge of the electron, r is the radius of the loop, and omega is the angular velocity. Now, I can rewrite this formula as minus e over 2 r cross v, where v is the electron velocity, e is the charge of the electron taken as positive, and r is the radial vector. Now, if we realize that r cross v is nothing but the orbital angular momentum of the electron divided by the mass, we can convert this expression again and connect explicitly the classical magnetic moment with the orbital angular momentum L. Now, if I haven't lost you yet, I can do something else, because the current flowing in the loop is simply proportional to the velocity of the electrons. So I can rewrite again the magnetic moment simply as I, the electric current, times the area of the loop, A, which I can also write in an integral form. To sum up, we have determined that a magnetic moment can be associated with circulating or rotating charges. That's fine. Now we can ask, what is the magnetic field associated with this magnetic moment? To do so, we make use of the Biot-Savart law that describes the magnetic field radiated by a current flow. This expression relates the element of magnetic induction field, delta B, to an element of current flow, delta I. Again, here mu0 is the vacuum permeability and R is the position vector. We can simply apply Biot-Savart law to the current loop associated with our magnetic moment. It gives the distribution of the magnetic field radiated by the magnetic moment. And this is what we get, a beautiful magnetic butterfly. In this picture, you should remember that the current loop that produces this magnetic field distribution lies in the center. You can also notice straight away that this distribution looks pretty much like the distribution of the electric field radiated by an electric charge. If we compute the magnetic field in the center of the loop, the magnetic induction is proportional to the current I, the area of the loop A, divided by A cubed, where A is the radius of our loop. If we place ourselves very far from the center of the loop, the magnetic induction adopts the same expression, but now with R cubed in the denominator. So the magnetic induction generated by the current loop decreases away from the loop. In other words, we have recognized that this field distribution is quite similar to the one we would expect for the electric field radiated by an electric dipole. Therefore, one could imagine associating the induced magnetic field to a magnetic dipole. And indeed, we can write the induced magnetic field as the difference between two dipoles, where P here is the fictitious magnetic monopole. And in this context, we can write the magnetic moment as the magnetic dipole analog to the electric dipole. Well, if you go back to Maxwell's equation, you might remember that the magnetic field is divergence-free by definition, which means that there is no such thing as real magnetic monopoles. Magnetic monopoles do not exist in nature. Nonetheless, the concept of the fictitious magnetic charges is very helpful to understand magnetism, especially magnetic textures in complex shapes. So it will be discussed in more details a bit later.
The third important concept I'd like to discuss is the distinction between the H field and the B field. If you are familiar with research in magnetism, you have probably noticed that the H field and the B field are used equivalently in the literature. Some communities prefer to use the exciting field H, while others prefer to use the induction field B. But what is the true difference between these two fields? Let me give it a try.
In vacuum, Ampere's law states that the current of the B field is proportional to the electrical current that flows in the system. So in other words, the B field is induced by a charged current, and that is why it is called the induction field. Alternatively, in vacuum, we can also define a magnetic field strength, H, which is simply B divided by the vacuum permeability mu0. In a magnetic material, Ampere's law is still valid, but there is a slight subtlety. What you see in this expression is that the total current contributing to the magnetic induction has now two contributions, the electrical current J as well as the so-called magnetic current Gm. So what is this magnetic current? We have seen previously that a magnetic moment can be associated with a current loop. Since the magnetic materials possess non-zero magnetic moments, one can define a magnetic current associated with each one of these magnetic moments. The magnetic current is what is called a bound current, so it does not transport electrons out of the system. In other words, its total flux is zero. Because of that, one can define a vector potential associated with this bound current, and this vector potential is nothing but the magnetization of the system. So then, in a magnetic material, if one defines the magnetic field strength H as B over mu 0 minus M, then we can rewrite Ampere's law as the curl of H is equal to J. So now you can see the difference between Ampere's law in vacuum and Ampere's law in matter. In vacuum, the induction field B seems more appropriate, while in matter the exciting field H seems more adapted. Notice though that because of this definition, the induction field B is discontinuous at the boundary between a magnetic material and the vacuum. Now we have two ways of looking at the same thing. The magnetic field strength, also called the magnetic exciting field H on the one hand, and on the other hand, the magnetic induction field B. To better visualize the difference between these two fields, let us consider a magnetic material. In this case, the magnetization points up and we apply an external magnetic field along the magnetization direction. The red arrows represent the magnetic exciting field H of the system. Inside the magnetic material, the exciting field is defined as B over mu 0 minus M. And for reasons we're going to discuss later, we call it HD. Outside the material, when there is no magnetization, the exciting field is simply B over mu 0. It is called the stray field and is written HS. It would be nice to get a better idea about the relation between HD and HS. To do that, we can draw a loop that encloses the edge of the magnetic material. Since there is no current flowing out of the loop, the integral of the magnetic field along the loop should be zero. Consequently, HD must be opposite to HS. Since HS lies along the B field, it means that HD must be opposite to the induction field B. This is why it is called the demagnetizing field. To make things more explicit, let us zoom on the magnetic material and look at the structure of the magnetic field inside it. The B field points up, the HD field, the demagnetizing field, points down, and the magnetization M points up. So basically, using the B field or the H field is only a matter of convenience.